Hi everyone. Today we're going to do a maths question under the Extension 1 syllabus in the topic of projectile motion. This question is considered a medium question and it involves a proof. So let's have a look at the question. A particle is projected to just clear two walls of height 7 meters and distance 7 meters and 14 meters from the point of projection. Prove that if alpha is the angle of projection, then tan alpha equals to 3/2. Then we need to prove that if the walls are h meters high and distant b meters and c meters from the point of projection, then tan alpha equals to h times bracket b plus c close bracket divided by bc. Okay, so the very first thing that we need to do is that we need to draw a diagram to reflect this. So let's draw a diagram, and I'm seeing if I can draw a straight line. So let's take a ruler and let me draw the base. And let's rotate this ruler. We'll have one height. Let's put it around here. And then we'll have another height around here. And let's finish this off by extending this a little bit so I can finish drawing the trajectory. Okay, so let me put in this line here. So if we have a look at the trajectory, the path that this particle takes might look like the yellow line. Okay, so right now this is 7 meters, and by the way, this is not drawn to scale, so let me write this down, and not to scale, and this is 7 meters, and this is 7 meters. So that means that this whole length is 14 meters. Okay, so this particle is projected from 0, 0 over here. Now, I want you to see that if we can manage to solve this part of the question, then all we need to do is to substitute the correct values for h, b, and c, and then we should be able to get this part of the question. So why don't we just tackle the harder part first, and then that'll automatically solve us the easier part. So let me just make it a bit cleaner. So let's tackle the harder part first. So to do that, we need to set up a few more variables. So rather than 7 meters, I'm going to write in the height, h, so h, and rather than 7 meters here and 14 here, I am going to write in b, and I'm going to write in c. Okay, so let's define the x and y's. So we all know from the topic of projectile motion that y double dot equals to negative gravity. X double dot equals to 0. Y dot is equal to negative gt, and we need to add in the initial projection. So the initial projection is this direction. Let's call the initial projection speed u. Okay, and it's projected at an angle of alpha. So this is negative gt, but when time is 0, the velocity is u sine alpha. Now why is it u sine alpha? Well, if I draw a little diagram here, if that's u, and then we draw, if this is y dot, and if this is x dot, and that's alpha, then I want you to see that sine alpha is equals to y dot over u. So y dot is equal to u sine alpha. So that means that x dot is very similar, is equal to u cos alpha. Y is then equal to negative half gt squared plus ut sine alpha, and that comes from integrating y dot, and x equal to u t cos alpha. Okay, so let's make this a little bit easier, and let's let g equals to 10. So g is gravity, which is 9.8 meters per second squared, but in this example, we're going to use let g equals to 10. So y is equal to negative 5t squared plus u t sine alpha, and x carries on the same. Okay. So where we go from here? Well, there are two conditions that are satisfied in this trajectory. So the first condition is that when x is b, y is h. Okay, so that's condition 1. And the second condition is when x is c, y is also h. So what we do is we take our equation that we have here, which is the equation of the line, and then we need to substitute out the t. So in this case, t is equal to x over u cos alpha. So then now we need this t to substitute into these t's here. So this gives us the flight path, regardless of what time it is. So then we have y is equal to negative 5 times, so we need to square that, so x squared over u squared cos squared alpha plus u sine alpha multiplied by the t, which is the bit in the brackets. So then this equals to negative 5x squared over u squared times, and you'll see why I'm doing this in a moment. I'm grouping this 1 over cos squared alpha by itself, plus now this u and this u can cancel out. This sine x over this cos x converts to a tan x. So this is x times tan alpha. This bit here is actually a sec alpha. So this equals to negative 5x squared over u squared times sec squared alpha plus x tan alpha. But then there's an equation where sec x or sec squared x is equal to 1 plus tan squared x. Okay, so the same thing applies when the x is an alpha. So this equals to negative 5x squared over u squared times 1 plus tan squared alpha plus x tan alpha. Okay, now let's substitute these 2 points into this expression. And what we'll have is we'll have 2 equations that we'll need to solve for the required tan alpha. So now I have this expression copied over to a new slide. So if you remember back to the previous slide, the 2 conditions were BH and CH. So let's substitute those values in. So let's substitute number 1. So when y is h, that equals to negative 5b squared over u squared times 1 plus tan squared alpha plus b tan alpha. And when we substitute the second condition in, we have h equals to negative 5c squared over u squared times 1 plus tan squared alpha plus c tan alpha. So what I want you to notice here is that the question wasn't asking for us to focus on u. Okay, we want to focus on the tan squared. So that means that we need to substitute out this u. So let's do that. So let me just get my pen. So how do we do that? We need to move everything to one side. B tan alpha is equal to negative 5b squared over u squared times 1 plus tan squared alpha. Then we divide both sides. Squared alpha is equal to negative 5b squared over u squared. Now let's then divide both sides by b squared. So then we'll get h minus b tan alpha over b squared 1 plus tan squared alpha is equal to negative 1 over u squared. So let's do the same thing for the other part. So likewise, we're going to have h minus c tan alpha is equal to negative 5c squared over u squared times 1 plus tan squared alpha. Then we divide both sides. So this 1 plus tan squared alpha is equal to negative 5c squared over u squared. Then we divide both sides by the c squared. So h minus c tan alpha over 1 plus c squared, 1 plus tan squared alpha is equal to negative 5 over u squared. I just realized that I forgot to put in the 5 on this side. I can't forget the 5. So now we can see that this and this are the same. So let's make this and this equal to each other. So I'm going to highlight that in yellow. We're going to make the yellow ones equal to each other because the red ones equal to each other. So now we have h minus b tan alpha over b squared 1 plus tan squared alpha is equal to h minus c tan alpha over c squared 1 plus tan squared alpha. Can you see that the 1 plus tan squareds will cancel? So in that case, we're going to have h minus b tan alpha over b squared is equal to h minus c tan alpha over c squared. Let's get rid of the fraction by multiplying both sides by b squared c squared. So then we have c squared h minus b tan alpha is equal to b squared h minus c tan alpha. Now let's expand. C squared h minus c squared b tan alpha is equal to b squared h minus b squared c tan alpha. So now, in this case, we want to try and merge this and this together because they have our tan alphas. So let's move these to the same side. So now we're going to have b squared. So I'm going to move this component over to the other side. So I'm going to have b squared c tan alpha minus c squared b tan alpha, and then I'm going to move this component over to this side, is equal to b squared h minus c squared h. And now we can factorize our tan alphas. So now we have tan alpha bracket b squared c minus c squared b is equal to b squared h minus c squared h. Now let's go over to this side. So we'll have a little bit more space. So now let's divide both sides by the bit in the brackets next to the tan. So now we have tan alpha is equal to b squared h minus c squared h over b squared c minus c squared b. Now we factorize the h from the top, and we factorize the bc from the bottom. Can you see that this top segment here can also be factorized because we have the condition that b squared minus c squared is equal to b plus c, b minus c. So that's just a factorization technique, or not a technique, it's just a fact. And if you need to do a rough check, just expand the bottom bit of the green and then you'll get back to the top bit. So now this equals to h b plus c, b minus c over bc, b minus c, and that equals to h b plus c over bc. And this equals to the proof that we needed to prove. And I've just brought that back in so we can see exactly that this is correct. So let's give ourselves a tick. So then we need to substitute the actual numbers to get the tan alpha equals to 3 over 2. So let's do that on this side. Make some space over here. Let's border it with yellow so that it's a little bit clearer. So then, if you remember, this condition is the condition where we have, instead of b as b, we have b equals to 7, we have c equals to 14, and we have h is equal to 7. So in this case, tan alpha is equal to the 7 times 7 plus 14 divided by 7 times 14. And if you put this into the calculator, you get 3 over 2. So I hope this video made sense, that some of these proofs may seem difficult at first, but if you think through and draw the diagram and think about what you're trying to solve, then the pathway could be a little bit more clearer. Hope you enjoyed this video and have a nice day, and don't forget to smile.